In this section I will discuss about the Faraday law of electromagnetic induction. What it states? It states that whenever the magnetic flux linked with a coil is changed, an induced EMF is produced in the coil, and it will last as long as the change in the flux continues. So this is the point about the Faraday law, and what is the mathematical form of it. The EMF is directly proportional to the time rate of change of the magnetic flux and is in the opposite direction according to the Lenz's law. Right, so E, that is equal to the closed path integral of E dot dl is equal to minus del phi b upon del t. Here in this you see that this is a coil and this is a magnet bar. When basically it moves forward and backward direction, it basically change the flux associated with this coil, right? And the two ends basically of this coil is connected with the galvanometer. So when the flux change here, right, associated with this coil, the EMF which produce inside it produce the deflection into the galvanometer. So this is basic idea of the Faraday law, right? So let us see how the Faraday laws can be converted into the differential form by using the Stokes theorem. So you have seen here that there is a open loop or a coil, right, a bar magnet, the magnetic flux associated with the coil if change, then an EMF basically produced inside the coil. This is the point. So it is not possible if you keep the bar magnet at fixed position, right? Here this is NS and this is E coil. If you fix it here and magnetic field lines magnitude is not changing, then no EMF will produce inside the coil. It will produce only when you move the bar magnet into the forward and backward direction. So that is shown by the d phi b upon dt, right? So phi b is the magnetic flux. First of all, we have to define the magnetic flux here. Phi b is the magnetic flux mathematically that can be defined as b dot ds, either with the closed surface integral or open surface integral. But now the point is here that how you will determine that. You have to consider here closed surface integral or the open surface integral. This is the physical situation. You know, this is a circular ring, a circular loop or a coil. The central part of it is open or closed. You know that is open. So it means the surface of the coil is open. So the area for the flux passing through the open surface. So which type of area you will consider, open or closed? Obvious, you will consider the open surface. So phi b is equal to open surface integral, this phi b is equal to open surface integral of b dot ds, right? So that is written here. This b dot ds with open surface integral is for the magnetic flux, and rate of it d upon dt, this If I differentiate it with respect to the time, it means flux is changing. Flux is changing, and because of that EMF is producing inside the current loop, right? That is defined by the closed path integral E dot dl. Why the closed path integral? Because you know this is a circular coil, right? And by changing the magnetic field, right, associated with it, it produces an EMF inside the coil. That means flow of charges. So because of the flow of charges, because of the current, an electric field will develop, right? By this way you can show, this is center of the coil, this is the electric field tangential to the circular path. Here this is E, like this way. If I consider a small segment here of this circumference, that will be dl. If I write it vector dl, then it will in the same direction as of the electric field, right? So E, vector E and vector dl both are parallel. So closed path integral of E dot dl, what it signifies, right? It signifies the EMF, the potential basically which develop across the ends of the coil, right? If this is the coil, so one end is A and second end is B, right? Like this way, number of turns. So magnetic flux is changing associated with this coil, and as a result the two ends of this coil, right, a potential difference will generate, and you can say that the current is flowing here. That is basically the Faraday law, but the purpose is that we have to convert this formula which is written here into the differential form, right? So what we are doing, we are just applying the Stokes theorem. Stokes theorem says that closed path integral of the vector E is equal to the open surface integral of the curl of that field del cross E ds, right? So in the left hand side the value of E dot dl here is equal to the open surface integral this del cross E dot ds, right? No ds, minus d upon dt and this b dot ds, right? So now you can see here that this is the open surface integral, this is also open surface integral. Now you can compare both the side, right? So this is, now one more point here, that this is the open surface integral b dot ds. Now let me know that this is the circular coil in which the magnetic field passes, right? So here what is constant? Magnetic field is constant or the area of this coil is constant? Obviously the area of the coil is constant, B is variable, right? So differentiation of B with respect to time varying magnetic field you have observed here. So this quantity basically comes into the left hand side by this way, right? So again there are two factors, one is in bracket and second is the area of the coil. You know that area of the coil is fixed, that is not variable, that cannot be zero if you are applying the Faraday law there. So this quantity may be zero, so either this factor or this factor is zero. Area cannot be zero, so you have this option that this quantity is equal to zero. when this del cross E this del cross E plus dB upon del T, this is del B upon del T, is equal to 0. And after simplification of it, you can see here that this can be written as one of the curl equation. Del cross E is equal to minus del B upon del T. So this is the possible way to convert Faraday's integral equation into the differential form. Here the integral equation is this one, and differential form you can see that is this one, del cross E. So curl of the E, it means that you had considered here this circular coil, right, and closed path integral of E dot dl signifies that this is equal to this. If you take the E tangential here, obvious tangential at this point, so this total, right, E dot dl over this closed path is equal to the, if you consider a small curl inside it and add to all them, then the sum of these curl will be equal to the this one, that is E dot dl, right, a pictorial view of that. Sum of these small curl, if you add, that is basically equivalent to this one, right. So this is the meaning of E dot dl, and you are writing here this E dot dl is equal to open surface integral curl of E I am writing again it, that E dot dl is equal to open surface integral. Sum integral means sum of the small curl del cross E ds, right. This is the meaning. So this was the possible way, right.